Hi guys, welcome to week 4, day 3 of CSI 41. And we're going to talk a little bit more about TDD today and the philosophy of it. I give this lecture at the end of CSI 40, but I know there's students that are in this class that didn't take CSI 40. And I also know there's students that were in CSI 40 that probably didn't pay attention. So let's go over TDD one more time. So, pull my PowerPoint here, enable editing. There, full screen. Don't need to call me out like that. Can quiz problem 2 be explained? I thought it was order n for a loop. Yeah. We'll talk about that after this. That's why I put a note on there that it was a trick problem, or kind of a trick problem. Okay, so your next homework assignment is going to be due on Monday. It's a really easy program to write. It's the kind of thing that you could write, I don't know, week 4 of CSI 40. It's fizzbuzz. It's traditionally you're given 15 minutes to do fizzbuzz during a job interview. You're supposed to be able to code this thing live, but it's a pretty good assignment for teaching people how to do TDD. So TDD is an acronym that stands for Test-Driven Development. It has become very popular in recent years in major software companies, and you can see I use it myself in this class. What I do is I post a bunch of test cases, and when you start developing your code, you're going to be failing the test cases, and as you develop your code, you'll start passing test cases. And when you fail a test case, it'll also say, you know, this is what you're supposed to print, this is what you did print, and that gives you a clue as to where bugs are in your program. And so that's the only difference between that and like how it's done professionally is that you don't have a professor who's handing you the tests, right? When you go on websites like LeetCode and Codewars and HackerRank and all these other websites, which I recommend, they give you good practice at coding. They're only unrealistic in the sense that you don't have to write your own tests. You can, like in Codewars, like there's an area actually where you can put your own tests in and things like that. But in reality, like I just hit submit, and if I fail a test or something, then I start debugging. Which I never do, of course, being a computer science professor. I get it right the first time, every time. So yeah, fizzbuzz is an easy assignment. It's you could even probably find copies of fizzbuzz online. I wouldn't. The whole point of the exercise, the whole point of homework is to do it yourself. But it's like 5 lines of code, you know. And so I added fizzbuzz 2, which is a version you can't find online because it's my own invention. Technically, it's my brother-in-law's invention. He proposed this homework assignment for you guys. My brother-in-law's a software engineer as well. He speaks at coding conferences and things like that. So TDD, what you would do if you're a real professional programmer is that before you begin work on a project, like let's say you're gonna, I'll just advance this slide. Basically you sit down and you write your test prior to writing your code. And this is a weird concept, right? Like, well, how do you test your code if the code doesn't exist? Well, yeah, you should start off failing all of your test cases, right? So if you've got a function that I don't know, is supposed to add up all of the elements in a vector, then you create a test where you pass it a vector with 1, 2, 3, 4 in it, and you say I expect this to return 10, right? And then you run your test and it fails. It should fail. If it passes before you write any code, you've probably screwed up your test. Like you put in a not equals instead of an equals. And I have done that before. Trust me. You actually want to make sure you fail your test cases. Because if you screw it up and you pass your test, then you're like, cool, my code's correct. And it's not correct. Your test is wrong. Right? So what you do is you start off by writing your test cases. And there's a science and an art to writing test cases. And so one of the biggest problems that students have in computer science is they only think about what happens when their code works correctly, right? So like if I'm writing code that averages all the numbers in a vector, right? And I pass in 1, 2, 3, 4. I want it to return, depending on if it's going to return a double or an int, which is actually a really interesting question. Let's say it's supposed to return a double. So I would pass in 1, 2, 3, 4, and I would expect that it returns 2.5, right? The average of 1, 2, 3, 4 is 2.5. And so I make that test. And then I make a test with other numbers, and I sit there with my calculator, and I figure out what the result should be for them. And I don't actually test any edge conditions, and I don't test any bad input. And that is a very common mistake that programmers make. What kind of edge condition would there be? What kind of boundary condition? What kind of problem could you imagine happening for that averaging thing, right? You pass in a vector of ints. What boundary condition could you guys think of that you should test that a lot of people wouldn't test? First time I hear it's okay to fail your test. Yeah, you should. You should start off failing your test. If you pass your test without writing code, then, I mean, sometimes you'll pass one like let's say before you write your code, you just need to return something, and so your average function just returns like some number, and that happens to be a test case that is expected like 0, right? Then you might pass a test case or something. That's okay, I guess. Is it a number or a string? So in your homework assignment, it's going to be returning a string, but let's just say that you're passing it a vector of ints, and it's going to return a double. Okay. What boundary condition can you think of for that? I can think of at least 2 that are obvious. Things that you should check for. At least 3 things. Good. So Edgerlin has one of them, which is you pass in an empty vector. Why would somebody pass in an empty vector to your average function? Well, you don't know who's going to be calling your code, you know? So the first thing your code should be doing is checking to see if there's anything in the vector, because if you don't, then you'll get a division by 0. And this is actually something that happened to me last night. Fortunately, you know, my edge detection brain was working, and I was averaging up things, and I'm like, wait, there's a possibility that there's going to be 0 things input to this. And so when you do an average, right, you add everything up, and then you divide by the size of the vector. If the size of the vector is 0, you're going to have a division by 0, and it will crash your code. So I added a check without crashing my code in that case. It did crash due to another reason. I didn't bounds checks I had a 2D array, and I went off the edge and crashed. But yeah, and so you want to test for those boundary conditions. So you want to check, will my averaging code work correctly if I pass in an empty vector, or is it going to explode? Bender said, what about negative numbers? Yeah, a lot of programmers forget about negative numbers, right? In the case of averaging numbers, the algorithm would probably handle it. Negative numbers fine. But a lot of code takes an int and just doesn't even consider the fact that there's negative numbers and there's 0, right? So there's actually 3 types of integers. When you take a vector of integers, there's positive numbers, there's 0, and there's negative numbers. And a lot of programmers just don't even consider the fact that there are negative integers, which are like, there's more negative integers than there are positive integers, technically. There's one more negative integer than there is positive integers. And people just don't handle it, right? Like, you know, like they'll write code where so like if you pass in 5, it'll count down from 5 to 0, you know? That's a fairly common way of doing a for loop, you know? They'll pass in a number, and it'll count down until it hits 0. And so if you pass in a negative number to it, it'll count down until it hits 0. Right? So you pass in -5, it'll go to -6. Are we at 0? Nope. Are we at -7? Nope. -8? Nope. Nope. Not 0. Not 0. And it goes all the way down to you know, -2 billion and change, wraps around to 2 billion and change, and runs until it hits 0. So 4 billion iterations later, it hits 0 and terminates. Or technically, because signed underflow is undefined behavior, maybe it runs forever, or maybe the optimizer just deletes your code. It's unclear what would happen. because people just don't think what happens if a negative number is punched in, right? And so for your fizzbuzz assignment, you have to, one of the things you have to check for is a negative number, right? Fizzbuzz runs from 1 to 100, and so if the user puts in -10, you have to return error, because people don't think about bad input enough. It's a common disease in computer scientists, is that we don't think about, well, what if it just is another not what I expect, right? And it's a serious problem, right? Like, there was an Airbus that crashed because its airspeed went negative, and the software system was like, oh, well, that's clearly an error. Airplanes don't fly backwards. But what happened was there was a gust, and this is and the plane crashed, right? Or the Boeing 737 Maxes were crashing because they have 2 pitot tubes to measure airspeed, and all the planes had them, but in software they were only reading from one of them. If you wanted to read from 2 of them, then you had to pay Boeing $100,000 for an extra 5 lines of code. And so Boeing literally sold a safety feature as a DLC for the 737 Max. They all had them, but it would only read from one of them by default. And so with the DLC, then it would read from both pitot tubes, and if one of them got ice in it, which would report a lower airspeed, then it would report a warning saying, there's a discrepancy in airspeed between the 2 pitot tubes, and the pilots would know what's happening. But what happened was, on these airlines that didn't purchase the DLC, ice forms in pitot tubes all the times, like 1 out of 1,000 flights, something like that. I don't know, 10,000. And often enough that it should not have been a DLC. So what happens when the ice forms in it is that if you only have 1, then the airspeed indicator, or the airspeed, is lower than what it should be. The plane thinks that it's going to a stall. It dips the nose to get more speed, and it actually takes over control from the pilot, and then the planes crash themselves. Like, the planes literally fly into the ground because they didn't consider what would happen if a pitot tube iced up. Right? The hardest thing in computer science is thinking of the things you didn't think of, right? And so, they probably figured the airspeed indicator was reliable, and then when it wasn't, people died. Hundreds of people died because of this bad mistake in software engineering. It was really funny. Like, prior to the 737 crashes, like, I saw some guy protesting saying, I'm a software engineer, I know your plane is safe. And I'm like, you're not a software engineer if you said that. Because software engineers are highly paranoid about all the different ways things can go wrong. And if you're that confident that you don't have any bugs in your software, you're probably a manager and not a software engineer, right? Like, it's, I've taken fault tolerant systems in grad school, I think, and there's a lot of ways of things can break. And so building a good fault-tolerant system is really hard. And the fact that Boeing had physically 2 different hardware airspeed indicators and was only using one of them, just, I literally, yelled at my computer when I read that they would charge for a redundancy in software. I was absolutely furious, because that should not have happened, and that was not the philosophy that Boeing had back in its heyday. Back in the heyday, Boeing had that paranoia about, okay, what if this goes wrong? What if this goes wrong? What if we get a bad input here? What if we get a bad input here? And now they're just like, charge them an extra $100,000 if they don't want to die, right? And, fortunately, Boeing's been punished for their mistake, right? Have you ever seen the parking lot in Renton, right? The Boeing parking lot is filled with grounded 737s, right? And Boeing's taken a huge loss for that. So maybe they'll start paying attention again. But they shouldn't have killed hundreds of people. It's just directly their fault, So I tried putting a string in the tester out. It gave me an error message, but I know my code can handle it. So we'll go over it. So with TDD, it trains you to think of those edge conditions, right? So, and it trains you. So there's 3 conditions. There's good, there's edge, and there's bad, right? And so good conditions are you pass in 1, 2, 3, 4, and the code sums them up, gets 10, divides by 4, and returns 2.5. Cool. Edge condition. You pass in 0 elements to the vector, and or you pass in, you know, negative numbers, or, you know, you pass in a lot of large numbers, and then you get integer overflow, right? And so and that was one of the other things I was going to tell you about, is that if you're adding up integers into an integer, and if you've got a lot of integers, it's quite possible you are going to exceed 2 billion, right? Even if your individual numbers are like in the millions, you know, if you've got an array of 10,000, you know, and they're all a million, you're gonna, you know, even though individually you're not anywhere near the boundary, if you've got a large array, they can easily overflow. And so you want to have edge cases. You want to test for, you know, overflow. You want to test for underflow. So add up a bunch of negative numbers together. See if you underflow. Add up a bunch of large numbers together. See if you overflow, right? And so that would be testing to see if your averaging code was using internally, because internally inside of that you might just have an int somewhere. And you might even be using 64-bit numbers everywhere, but if one of those numbers in there, like the int temp equals running total plus the new thing, that will overflow, right? And so you have to test it. You have to test your code for 10,000 and millions in a row. You have to test it for 10,000 negative millions in a row. You have to test it for an empty vector, and you have to test it for, you know, just the regular cases. Just come up with 10 or so regular cases. And then you start by failing all the test cases, right? And so you start red. Red means you fail a test case. And then as you write code, you'll start passing test cases, and they'll turn green. And a lot of times when you get your code mostly done, you're going to pass 8 out of 10 test cases, right? Because once you get the adding and the averaging done, you're going to start passing test cases. But then you're going to fail a few of the edge cases. Like, for example, you might return 2 instead of 2.5, because internally you're holding it in an integer, and then you do the division by another integer, and so you do integer division instead of double division. So that edge case you fail, and you're like, oh, I have to go back in there and cast it to a double, so I do double, floating point division instead of integer division. Boom, that one turns green. You run your test case over and over again. And then you're like, okay, I'm failing these edge cases. Oh, shoot, with an empty vector, it's crashing. Okay, fix that. Special case and empty vector. Okay, now check for overflow. Oh, shoot. All right, I'll change the internal sum into a 64-bit int instead of a 32-bit int. Okay, well, that passes now. Oh, wait, that really big one, it's still overflowing. Ew. Maybe I should be holding in a double. I don't know. And you have to, sit there and think about these things. And then once you pass all of your test cases, then it's called going green. Red means you fail the test case, green means you pass it. And then once all of the test cases are passed, your code's correct, right? But it's probably pretty ugly at that point, because you might have a lot of special cases in there and stuff like that. And so you do the third step, which is called refactoring, where you do a once over on the code. For example, let me show you Codewars. Why is this screen just not? I'm trying to click on this thing; it's just invisible. Oh, there it is. Okay, cool. So let me go to Codewars, and let me give you an example of what refactoring looks like, because you guys might not know. Potato Bun is ahead of me. Oh, Potato Bun. Okay, kidding. Refactoring is polishing. Yeah, that's another way of putting it. But it's important that you run your tests again after you refactor it, because you want to make sure you didn't break anything. It's very possible to break things when you refactor. So this is okay. So let me pull this up here. So this is called Codewars, and it's a great way of practicing your skills. I highly recommend it. I can post a link on Discord. I was working on it over winter break to keep my skills up. I don't like going too long without programming, because you start getting rusty, and your skills decrease, right? So I like to use websites like HackerRank I used in the past, but I really like Codewars. It's not really a war; it's just a practice site. And so for this assignment, you have to write a function called format duration. They pass in a number of seconds, like 3,662, and you have to output the string 1 hour, 1 minute, and 2 seconds. Okay, and then it has the rules on the formatting and things like that. So here are the test cases. Look down here. So So test case, if you pass in 0, it should print now. If they pass in 1, it should print 1 second. 62 should be 1 minute and 2 seconds. So it comes with some test cases, and you can add your own, and they encourage you to write your own test cases. And you can hit test here, and then it will run these 5 tests on your code. It compiles it, it runs it. Green, I passed all the test cases. Cool. So what happened was I wrote this function here. Oh, this is my final version. Dang it. Past solutions. There we go. Okay, so let's see if I can hide this. Yeah. It's not letting me hide this. Well, there we go. Well, that'll work, I guess. So my first version was this long, and so what it does is it basically, I computed how many seconds are in a year, how many seconds in a day, how many seconds in an hour, so on and so forth. Yeah, no, this is my first one here. Okay, and so basically I was doing a bunch of divisions. So I'd divide by how many seconds in a year to get how many years there were, and then I would subtract out those many seconds, and then I would figure out how many days there were in the remaining seconds, and then I would subtract out that many seconds, and I did that over and over again. And for everything that was going to be printed, like years, days, hours, whatever, I kind of counted that. And this is actually a fairly clever line of code here, where I'm saying years is equal to. So I actually have a single equal sign inside of an if statement, which is legal. It's usually wrong, but in this case it's right. So what I'm doing is I'm setting years equal to seconds divided by seconds in year. So if there's like 3 years, then it divides seconds by number of seconds in a year, it gets 3. It sets years equal to 3, and the single equals operator returns a thing of the same type. In an earlier lecture, I used void as the return type for an operator equals, but that's actually not how you're supposed to do it. It's actually the equal sign, single equal sign, is supposed to return a variable of the thing that got assigned. And so in this case, if I set years equal to 3 years, then it should also return as an expression the value of 3. And so that would be true, because 3 is true. And so basically what it's saying is if there were any years, add 1 to the number of things that I'm going to output in the output string. Like 1 minute, 1 hour, 2 seconds, that's 3 things. Okay. Yeah, this is just what they gave me, right? So that's the function signature they gave me. I do have using namespace standard because I get annoyed by typing it, but that was actually provided by Codewars. And so I do this over and over again, and it worked fine. It worked fine. And then I refactored this because I realized this equation I just keep doing over and over again, right? Like this pattern, I just keep doing over and over again. I didn't really like the look of it, so I refactored it to be a function. So the function does that. It divides the number of seconds by the number of seconds in a year, and it passes in things to print, and then basically it sets years equal to basically seconds divided by seconds in year, and then if the result was positive, it adds 1 to things to print. And so this code here is a lot nicer looking than this code here. It does the same thing, but that's an example of refactoring, which is my point of showing this to you. So by refactoring it, I was able to get this, which has a lot of parentheses and equals and minus equals and times and things like that, and plus plus. Like this is a pretty gnarly line of code there, right? This has an assignment inside of an if statement after a division, and then if that assignment was true, in other words, something happened, then it increments things to print. Like there's a lot of stuff happening on that one line of code, and so I refactored it to just be a function, right? So we're going to pull how many years there are out, then we pull how many seconds there are out, then we pull our days we have out of seconds, then we pull hours out, pull minutes out, and then seconds remaining. And then I just have a function that that prints, that adds to a string. So if years are positive, then it adds 3 years to the string that's going to be returned. If days are positive, then we return days and things like that. So you might notice that I'm not bounds checking for negative seconds, right? And this is something that hurt my soul a little bit. But the assignment says you do not need to check for it. So I'm like, all right, but it hurts my soul a little bit, right? Because why not make it an unsigned integer, right? If you want it to be 0 or greater, it should be an unsigned int, maybe. I don't know. But like my code will not work. My code will not work with negative numbers, and it hurts me like on the inside, right? To not handle it, because ints can be positive, 0 or negative, but the instructions say don't worry about negative numbers. It's like, all right, but that's the mindset a lot of programmers have, is that they just don't consider negative numbers. You know, it's an int. Ints can be negative. If I was making this assignment, I would have said if you pass in negative seconds, just return error, right? And like that's one more if statement, and then your code doesn't explode if you pass in a negative, right? So, so in fizzbuzz, yeah, good tests would be 3 and 5 and 15 and 20 and 21 and 42 and just things in the middle somewhere. Edge cases would be 1, right? Because that anytime you have an if statement, if you say like if x is greater than 5, then your edge cases are going to be 5 and 4 and 6, right? Anytime you have an if statement where there's a dividing line, you want to have a test case on the dividing line, 1 to the left and 1 to the right, ideally, right? Because a lot of times people get that wrong, and so most errors crop up right on the edges of the problem, right? So if you have a 2D array, you're trying to set each point to the average of the points around it. Most students' problems aren't in the middle, right? Most students know how to read the array value above and below and left and right and add them and divide by 4. Most can do that. It's the corners, right? Because in the corners you only have 2 neighbors, and so you have to add. You have to make sure you don't read off the edge, or it crashes your code. And if you're on one of the sides, then you read 3 values. Like if you're on the left side, you read to the right and up and down, but not left. And so you have to divide by 3. And so those edge conditions are where bugs usually lie. And so I actually break out my tests into good things, which would be in the middle of the 2D array, edge cases that are on the corners and edges, like literally an edge in that case, right? But edge cases more broadly mean anytime you got a boundary condition, right? If age is greater than 40, then do something. Okay, I'm going to test my code with an age of 40, 41, and 42. Right, because between 40 and 41 is the boundary. I might even test 39, right? And I'm just going to have a lot of test coverage on anytime there's a line in the code to make sure I don't have an off by 1 error. Off by 1 errors are the most common kind of error that that people make. Where like last night I wrote code to put a tag on CD edgelord reference. So last night I wrote code that would print tags like the name of a country over the country. So this is the country of Las Vegas, the country of Brussels, got Kabul over here, Madrid. It randomly generates a map, right? We got Carthage in the middle there, and country of New Orleans, of course. And so if Hong Kong conquers New Orleans, then the label, the tag, moves to the center of the region. But you can see that there's an off by 1 error here, where the label, like right here, Prague is 1 spot to the left of where it should be, right? The requirement for the homework assignment is you have to put the label in the center part of your country, and if there's no room in the center part of your country, then find the nearest spot to the center part of the country where you can print the whole name of your country. And if you can't find it, if you can't find any spot, then don't print it at all. Okay. And so you see how Vegas moves to the center. But here it's off by 1. It's 1 square to the left of where it should be. Okay, so that's an off by 1 error. And even programmers like me will make off by 1 errors. It's very common. Very common. And so that would be an edge condition. Like test a scenario where the label would print right on the boundary of the country, and make sure it's in your country, not 1 square outside of your country. That's a boundary condition. That's an edge condition. Okay. And so that's kind of stuff we do in IS50B, by the way. So IS50B, we do a lot of programming for games. And so you can almost think of it as bonus computer science. Like after you finish all 4 semesters of computer science with me, you can take IS-50A and IS-50B, and that will give you extra programming experience. I've got some of my best former students in there right now, and they're learning new stuff in computer science from it. So that's TDD, right? So TDD is you write your tests first, you pass the test cases, and then you refactor. So I came in here and I started with this, and also in here you can see I've got some ternary operators in here. So if years equals to 1, it prints year, otherwise it prints years. If days equals 1, it prints day, otherwise it prints days. And so 4 courses, 40, 41, 26, and 45. So 40 is learn to program, 41 is data structures, which we're going to go over today, actually. 26 is discrete math, which is all the math you need to know as a computer science major, more or less. Things like also how to like find shortest paths, things like that. And 45 is assembly programming / learning about computer architecture, like learning how actually a CPU works and how the memory subsystem works and all that kind of stuff, because that makes you a much better programmer as well. And after you finish those 4, it's fairly common for students to take IS-50A and IS-50B with me, which is game development, partly because making video games is a lot of fun, partly because it just gives you more experience programming. And I run IS-50B as a, you're going to learn more advanced stuff in computer science. It's fun. So Muya is in it right now, so he can tell you about it in text. So any shortcut for that function call in the library? I don't know what that means, but yeah. So so I replace these ternary operators here with just passing in year, and then the function itself will adds a s, because I realized that all the plurals are simple plurals for this. Originally I used the ternary operator because it's like, what if I don't know, day ends in a y and then it has to turn into ies, and I was like, wait, days just turns into an s also. And so I ended up just realizing I could just tag an s onto any of the quantities, and so I didn't need to do all that stuff. I could just make it like this. And so that's what I mean by refactoring. So with refactoring, you come in and you clean it up, and you find redundant things that you did and remove the redundancies, or make a new function that kind of lets everything look cleaner and stuff like that. And then you hit run again and you make sure you pass all the test cases, then you're done. And one of the really nice things about TDD is when you are done. You have a definition of done. The definition of done is you're passing your test cases. And if you're passing your test cases and your code isn't done, then your test cases weren't good, right? And so you need more test cases. And so that's why imaginary homework, by the way, had 20 test cases, was because over the years, students would find, like I would find bugs in my students' code, and there wasn't a test case that was detecting them. And so every time a student would submit correct code that actually had a bug in it, I would make a new test case and name it after them. This is the Navarro test case. And it's not like I would knock their points off, but it would be added in for next time. And so every year that I've done imaginary homework, the number of test cases has gone up and up as I found more and more ways that students' code wouldn't work. And that's why in imaginary homework there was a lot of 18s and 19s and 20s in terms of passing test cases, was because you could write code that was good most of the time, but there was some little edge case in there that you weren't considering. So a lot of students were just like, good enough. I'll take the 9.5 out of 10. So okay, so you start with red, you go green, you refactor. The benefits are so a lot of professional companies now, if you want to add your code to the code base, it'll actually run all the tests on them first. So it'll actually reject patches. So like if you're trying to submit new code that will go to production, if your thing breaks anything, then it gets kicked back to you and it won't get accepted into the system, right? So there's a validation process now. There's like Jenkins and continuous integration and all this kind of stuff that basically helps prevent you from breaking production code, right? So the downside is it does slow down your build time, because if you've got a lot of tests, if you've got like 100,000 tests, sometimes you won't run all of them. You'll run like a smaller subset of the tests, and then at night, the nightly testing system will do the full set of a test suite. And so you might have to wait a day for your code to go to production, because you want to run all the tests to make sure you're not breaking anything. And then also maintaining tests takes time. Like if you change how your program's supposed to behave, like if you change it so you're supposed to return an integer instead of a double when you do the averaging, all of your tests are wrong now, right? And so if you were before saying, okay, you should return 2.5 if you're adding up 1, 2, 3, 4, and if you change what your program's supposed to be doing, like it's 2 now, there's going to be a lot of test cases that are now wrong, and you got to go through there and fix them, and so updating tests is kind of a hassle, you know. And it's easy to do unit testing. It's easy to like test like a function and make sure the function's doing what it can. But like usability testing, it's like kind of impossible to do. Like, is the website easy for people to use? Like, you can't really test that. Things like in a video game, like if I shoot a laser guided rocket, does it track the rocket properly? Yeah, that's kind of hard to make a test for, you know. Like, you could probably do a test for the function that does the math to see if it'll orient itself towards the dot. But like, as far as like full end-to-end testing in a video game, like there's a person running around and I shoot it and it's a heat-seeking missile and it chases it, like, you're just gonna probably just have to test that the old-fashioned way, you know what I mean? So GUIs, usability, that kind of stuff, it's harder to test. Okay, so, and sometimes, like if you have a test that relies on a database, then you have to create like a fake database. You have to do a mock database that'll simulate, you know, sending you data, and you have to do things like make it simulate the database going down, or the database occasionally taking a long time, and so you actually have to end up spending a lot of time just like setting up fake data sources and things like that. So I teach 26 in the fall and 45 in the spring. Yeah, so you have to take 40 and 41, and then you can take either 26 or 45 after that. You don't need 26 or 45. Yeah, but you really kind of do need this class for 26. It didn't used to be that way, but I just noticed a lot of students struggling. Okay, so I added 41 as a prerequisite. Okay, so yeah, CD, fizzbuzz, TDD. So for this assignment, you're going to have to write tests. So good tests, you know, are just normal operation. Bad tests would be if the user types in 200 or if the user types in negative 200. Okay, because I want you to get into that mental habit of realizing you might not always get what you expect. Like in that Codewars code, it's like just assume that seconds is going to be 0 or greater. It's like in real life, there is no guarantee that somebody won't call my code with a negative number, right? Either a malicious user might do it, or just you might call it accidentally with a negative number. It's an int. It could be negative, right? And so I want you to get into the habit of checking for bad input, okay? And handling it properly without crashing or infinitely looping. I really hate my code crashing. I really don't want my code to crash. I really don't want my code to run forever, you know? Okay. It's a different form of immortality. Your code runs forever because it's in an infinite loop, right? And then there's edge tests, which edge cases where, you know, when there's if statements, you're on the boundary of things, right? So 99, 100, 101, 0, 1, 2. Anytime you have an if statement that says if their age is greater than 65, do this, you know, and then you pass in 65, and then you go, oh, oops, it's supposed to be greater than or equal to 65. You know, very common mistake. And then you're going to do fizzbuzz 2, which is the same as fizzbuzz, but you can't copy and paste the code online, which you shouldn't do anyway. You should write it. It's 5 lines of code or so. But this is a variant of fizzbuzz called fizzbuzz 2 that my brother-in-law came up with, and then you have to write test cases for fizzbuzz 2 as well. And then when you run your program, you can run fizzbuzz, you can run fizzbuzz 2. You just type in a number and it'll print both the results for fizzbuzz and fizzbuzz 2 for that number, like 50. It'll print out buzz, right, because it's divisible by 5. And then test will run the Google Test Suite. So if they type in test, then it will call the Google Test Suite and it'll run all of your tests and tell you which ones you're passing, which ones you're failing. Okay. Are you going to be remotely on 26 and 45 in the future? Unclear. It's unclear right now. I think the fall is definitely going to be online. I don't see us being back in person in the fall. 45 though next spring. We're hoping we'll be back in person. I read a story today saying the pandemic is going to go on for 7 years. At the same time, the COVID cases are down 30% from where they were 3 weeks ago. So there's been a huge dip in COVID numbers. Who knows? And it's probably not even due to the vaccine, right? Like, only a few percent of Americans have been vaccinated. So, who knows? I do not predict the future. But I will tell you that the school is currently planning on synchronous for fall. Synchronous meaning there's a fixed class time. And the reason for that is if we want, we could convert that to in-person because all the times are fixed. Right now it's all asynchronous, so there is no fixed time for a class. But I like having a time that I'm recording my asynchronous stuff so that you guys can ask me questions because it seems a lot more interactive that way. And I don't like lecturing to an empty room. Okay. In fizzbuzz 2, will the original fizzbuzz requirements be tested and then the new case? Yeah, that's a good way of thinking about it. Because fizzbuzz 2 is fizzbuzz plus a couple extra things as well. But some of the test cases will be different, right? So if you pass in 23, 23 normally would be 23 in fizzbuzz. But for fizzbuzz 2, because you add the 2 digits together is the difference. 2 plus 3 is 5, so that would be buzz. Okay? So you have to handle... you can copy and paste the test cases, but you have to think about which ones are going to change. You can't just reuse all of them. And then this is the important thing, guys. Copy your tests and paste them into Canvas. So there's a spot on Canvas where you can paste your tests, and I will look at those and give you points based on it. So a quarter, I believe, of your points are based on your tests. You need 5 test cases in every category. 5 here, 5 here, 5 here, and then same for fizzbuzz 2. And you might be like, well, I can't think of that many bad test cases. There's only negatives and numbers too small, numbers too big. I don't care. Just make up more. 400, 500, I don't care. Just make sure you've got some negatives. You get, negative 200, positive 200, negative 400, positive 400. But try numbers also not divisible by 5, negative 401, whatever. Is there no sound? Test, test, test. You chose all of the not safe for work numbers. Yeah, you're not going to offend me. So. It's fairly common for computer science students to pick 420 and things like that as their test numbers. Okay. So any questions about fizzbuzz? It's designed to teach you TDD, the TDD methodology. Okay. It's not designed to be challenging technically, as far as like actually writing the program. The only thing you should keep in mind is the toString function. Okay, so if you pass in 5 toString, this will create a string, right? String s. And so this will set s equal to string 5. So that's the only technical thing that you guys might not know. toString. Everything else you should be able to handle, no problem. Hello, hello, hello. Hello. Turn up the gain, maybe. You can hear? Huh? Weird. I don't know why. Like Discord will cut out sometimes for people. Okay. but yeah, toString is the only technical thing that some students might not know, and that converts from an int to a string. Okay, so that's enough of TDD. Let's not save that. Nope, I just saved it. Well, whatever. It's all good. So if you want to do stuff like this is edge detection, as far as it's finding the edges of the boundaries and things like that. Then take IS50B, or 50A first, and then B. All right, so let's talk a little bit about data structures. So our topic this week is really the standard library. And there's going to be like 5 or so major data structures we're going to cover in this class. And you should have learned them already on Zybooks. But let's just go over that real fast. Check for duplicates. Oh, right. So Ephraim was asking, why was the second question on the quiz not order n? Okay, because I thought if you have a for loop, it's going to be order n. What makes this order n is this. The size of the vector is n, right? The size of the vector is n. So that means this loop will run n times. It is proportional to the size of the input. The input size is vector.size, right? N is vector.size. For the quiz question, it was this, 10. So if the vector is size 100, if the vector is size 1,000, if the vector is size 10,000, the amount of iterations you do does not change. And so this makes it a order 1 algorithm. Order 1 doesn't mean it's one operation. It means constant running time. Remember, order 1, there's always a secret k that you can multiply things by. And so if it's 10, the k would be 10. But we don't write that down. What we write down is order 1. It means the running time is flat. Now, some constant running times are very low flat. Some are very high flat, like 10. No, maybe 10's not even that high. Like even this is constant running time. It just has a much higher running time graph. It's flat. There's no slope on it, right? And so even though I'm doing 1,000 iterations, this is order 1, because as the vector gets bigger, as the vector gets smaller, it does not change how much work is being done. And this is a very that's why I made a quiz question for it. It's because students will just look at the for loop and be like, it's order n. It's order n if it's actually doing n work, right? In this case, it is doing the same amount of work no matter how big the vector is. If the vector is a billion, if it's a trillion, if it's a quadrillion, it doesn't matter. It will do 1,000 operations. So this is constant running time. Okay, and it does not change. So that is a constant running time. So this whole thing here would be order 1 times order n times order 1 times order 1. So this whole loop now would be an order n loop. Even though it looks very complicated, the highlighted code there is an order n operation. It is linearly proportional to the size of the input. And it's going to be 1,000 times n, right? So it's actually going to be it's a much sharper, let's see, from your perspective, yeah. So it's not, a slope of 1, it's a slope of 1,000, but it's still linear, right? And so for a large enough n, this would actually be faster than n squared, even though it's got a much sharper slope initially. By the time n exceeds 1,000, then it's going to be faster than an order n squared algorithm. Okay, so put this back in here, vector.size. Okay, so copy main.cc to public big O.cc CHP. So if you guys want to look at the notes for that, it's going to be in this file here, public big. It won't let me type. There we go. Okay. Warning: this could be considered a trick question by some. Yeah, I don't like doing trick questions. When I give you guys the daily quizzes, they're literally just what I went over in class. Like if I say that a makefile does not speed up your initial compilation, but it speeds up your subsequent compilations, then that's the question on the quiz. right? There's no hidden subtleties and meanings that I'm there to get you. And if I am going to do something that looks tricky, I will actually put a disclaimer on it saying, warning, this looks like a trick question, or it could be considered a trick question, right? But it's not a trick question, right? So could you go over again the sound? So if you have a constant number here, if you have a constant number there, then it's constant running time. Because the number of times the loop runs does not change based on the input size. What big O is about how does the running time of the algorithm change as the vector gets bigger. If vector gets bigger, you've got the input size, you got your running time. What's the shape? Is it a line? Is it flat? Is it a curve? Is it a logarithmic? And so with a loop doing 10 times, that's constant running time. It's just doing 10 things. And that's why I said, like, I didn't care, like this part here, I was considering that one operation, even though there's actually 5 different things happening there. Like whenever you do an array access, there's a pointer and a addition time and a times, because times the size of the array plus j, and so there's like 2 adds and 2 multiplies and a comparison happening right here. But it's still just order 1, because it's always 5 comparisons. It doesn't matter how big the vector is, it's always 5 comparisons to do that step, so it's order 1. So so even though that is much faster than that, this is 5 times faster. We don't care about things like 5 times faster. When dealing with big O, 5 times faster, who cares? We don't care about fiddly details like 5 times faster. What we care about is it constant running time, or is it linear, or is it quadratic, or is it exponential, and things like that. So big O is a very crude way of talking about performance, but it's also usually the most important, right? So if you have a sorting algorithm that's order n squared, I don't care if you make it 5 times faster. Like, I don't care if you make an order n squared algorithm 5 times faster, because by the time you're sorting like 1,000,000 elements, you're already 1,000,000 times slower, or 50,000 times slower than you should be. So if you can make your bubble sort 5 times faster, cool. You're still 10,000 times slower than if you just called sort. Okay, and that's only for 1,000,000 elements, which isn't even that much, right? And so for big O, this is computer science is more than programming, right? And so computer science has a lot of math and logic and things like that in it. And this is a big part of computer science, is just understanding the running time of algorithms sort of in a broad, big picture perspective, right? And then when it comes down to it, you'll actually run your code and time it and see how long things actually take in practice. But big O is what we start with, right? If you have 2 options for an algorithm, one being order n log n, one being n squared, like for sorting, for example, you would not pick the order n squared one, except in very limited circumstances. So one of the circumstances where you might use bubble sort, for example, is if you're expecting your array to be sorted or very close to sorted, bubble sort will actually do better than regular sort. The reason for that is because bubble sort will just iterate across the entire array, and if it's sorted, it's done and it returns. So the best case time for bubble sort is actually order n. So if you hand bubble sort a sorted array, it'll just go down and be like, yep, it's sorted, and it's done. And if there's only like one person out of place, then it can actually bubble it down into place and then return, also in order n time, depending on how you have it written. And so if you have a sorted array or an array with like one element out of place, then bubble sort will actually be faster than quicksort, because quicksort starts off by randomly shuffling all the elements in the array, because quicksort normally works very, very badly on sorted arrays. Quicksort actually has a running time of order n squared if the array is sorted. And so you don't use quicksort on a sorted array, you use bubble sort. So if you somehow know that your array is going to be sorted or only has one person out of place, then yeah, use bubble sort. So there's specialty circumstances like that where we don't worry about worst case time, but best case time, right? And so big O is just kind of the starting point. There's best case time, there's worst case time, there's average case and exact case. This is your starting point into the adventures of algorithmic analysis. Computer science. Wait, it's all math? Always has been. Yeah. So computer science is an outgrowth of math. So my department was actually in the math building, right? And we were in the applied math building because computer science at my college was a division of math. At Berkeley, Steve Wozniak was a computer science or computer engineering person. And you couldn't even take computer science classes as an undergraduate. They didn't think you were smart enough to take this class. You had to be in grad school. And so, so you had to join math with a emphasis in computer science, right? And this would be in the 70s, I think. Computer science started at Purdue in 1964, and Stanford also, I think, in 1964. And so it's not really even that old a discipline. I took it in the mid-90s, and we were separate. We were a separate division, we were a separate department, but we were still in the math building. It's a very gloomy concrete building. And while I was there, we got funding to make our own building, and so I participated in the design efforts for the computer science building at UC San Diego. And the one thing I really wanted, I got, which was a graduate lounge, because the original plans had no graduate lounge in it. And graduate students, trust me, we live in these buildings. We need a place where there's a couch you can sit down or lay down, and a fridge where you can have some iced tea or whatever in it. Like, you need an area for grad students to socialize, or we will go absolutely crazy. And they didn't have it in there, and so I pushed, and I believe that got put into the final draft. My second choice, though, was the hot tub on the roof. They didn't do that, unfortunately. I lobbied hard for a hot tub on the roof, because it was right next to a canyon, so you could sit there, like, look out over these canyons, and I thought it'd be pretty fantastic. But for some reason, they didn't want to spring for a hot tub on the roof. So, yeah. I hate math classes because they punish you for getting ahead of the class. Will there be a lecture on Monday and Friday next week? What's next week? Is it a holiday or something? We don't lecture on holidays. Okay. So let's talk about the standard library. All right, standard library time. Data structure time. All right. I removed main.cc, right? Okay, good. Then main.cc. So let's talk about standard library and data structures and the differences between them. So you all know vectors, right? Then there is a type of data structure called a list. Okay, a linked list. And your next programming assignment will be making a linked list, but for now we're just going to do it conceptually. Okay. So a linked list is you can think of it as like a necklace or something like that, where each individual element in a linked list has a pointer to, this is a singly linked list. Let me find a doubly linked list. Here we go. So every let's say you're making a linked list of integers. So if you store the number 5, cool. And then if you store another number after it, then what it does is it has a pointer from the node holding 5 to the next person, and the next person will have a pointer, like let's say we store 6. 6's node will have a pointer backwards at 5. And so it's like a necklace, right? Like beads on a necklace, right? And this is a singly linked list. It has just next pointers. It doesn't have previous pointers. And so as you append things to it, then the data structure just grows and grows and grows and grows and grows. The benefit of this over a vector is that vectors, when they run out of room, they have to do a reallocation, right? And linked lists, you don't have to do that. At every time you append something to it, it just news memory and has a pointer to the new person. And so vectors have to do reallocations occasionally. Linked lists don't have to. Linked lists, you can also do things like adding something to the head of it, right? So if you want to add something to the front of a linked list, you can do that in order one time. You make a new node, make that the new head, and have it point to the old head, and that's an order one operation to add something to the beginning of the list. Whereas with vectors, Vectors, it's an order n operation to add something to the beginning because it has to move everything to the right to make room for it. So vectors are contiguous blocks of memory that occasionally will reallocate, and a linked list is each individual thing is newed separately. So pure math is proof. It's contrary to the spirit of computer science. We're built on shortcuts. Yeah, we are. Computer science is for lazy people who want to be productive, right? I don't type hello world every time. No. I have a macro for that, right? Everything that I can automate, I automate, right? So let's take a look at the difference between a linked list and a vector, right? So you can say vector. You can say vector. Do I have caps lock on? What's going on here? Vector of int named vec, and I can initialize this to 1, 2, 3, 4. Okay, and I can say list of integers named list. Nah, let's not call it list. Liz. Okay, is equal to 1, 2, 3, 4. Okay. Looks the same, right? Do they both hold the numbers 1, 2, 3, 4? Yep. How do we print all the elements in a vector? For every integer x, I don't like using I. I usually means like a loop iterator, you know? So I usually use x here. For every integer x in the vector, cout x. Little note here, cout vec. And then Liz. And you can see we print them out exactly the same way. All right. So one of the really nice things about the design of the standard library is that most of the data structures, you can build them the same way, you can output them the same way. In fact, if I change just the word vector to list, you can see it'll like you won't even notice any difference, right? Like if I were to just make this vector a list and run it, I didn't have to recompile any of the code. You know, like 80-90% of standard library container types, which are data structures, are just interchangeable like that. Okay, it's really nice. So even though behind the scenes the list has these pointers and it's newing things and gluing things together like beads on a necklace, from a C++ perspective, it's like, yeah, for every element in the list, print it out. And the reason, and that's why we have these things like iterators, because like you'll you know, ranges and all that kind of stuff. Most of the code will work with them. Like if I want to count cout number of fours in vec, then I can see out the count of vec.begin, vec.end, the number of times the number 4 appears. Right?
Just a warning that you typed cout instead of count.
I did. Thank you. Muscle memory. Thanks, sir. And that's why we pay you the big bucks. And then we can do the same thing in Liz. 3s Liz and dot. And there we go. And so there's 1, 4 in vec, there's 1, 4 in Liz. You guys see that? Like, kind of cool, huh? Okay. And so if you're using a list, like I said, your next assignment will be making one, but if you're using a list, I don't know. Looks pretty similar to me, right? Now, let's see if we can find something that lists can do that vectors cannot. So what if we do list.push front and put the number 4 at the front of the list? Can we do that with a vector? do vectors have a push front? Do they have an option to add something to the beginning of the vector? What do you guys think? Will that compile? If I let's see, let's separate this out a little bit. Let's see here. Can I do vector dot push front? Will that compile? Nope. Vectors do not have a push front. They do not have a pop front. You cannot push or pop easily to the beginning of a vector. You can use insert. So you could, if you really need to do that, you can use insert, and you can insert at the beginning, the number 4. But the reason why they did not put push front in there is because they don't want you writing an order in thing by accident, right? This is the big benefit of a list, is that lists can push and pop off the front in order one time. Vec.insert, what would it be? Vec.begin 4. Let's see if this works. This is a order in version of push front. So they actually deliberately made a decision not to have push front and pop front on the vector, because if you were to do something like because you can usually swap these things out, right? They want it to break. They want it to break. Like, shouldn't be doing that. You should not be doing that, because what would happen if you switched? Oops. What happened if you switched out a vector and a list in that way is that your code would go from order one time to order n time. And that's why I'm saying big O is part of the common parlance, right? It's order n because it has to make room at the beginning. In order to make room at the beginning, you have to move all n elements one to the right. And so there are some things where they are incompatible, and they're deliberately incompatible. They're deliberately incompatible because they want you to look at that. Like if you were just like, oh, let's time the code differently. Let's just switch it from a vector to a list. Boom, it breaks, because it's like, we want you to look at this. We want you to pay attention to this. And if you really want to, you can switch out that with an insert if you want. But we want you to not accidentally slow your code down. One of the big design decisions in C++ is that C++ should be fast. We aren't Python. We're not Java. We're C++. Speed is, we are speed, So if you want to be slow, and do an order and insert, knock yourself out. It's right there. You can do it. That'll put a 4 at the beginning. Right. So if we compile it and run it, you can see there's now a 4 at the beginning here. There's now 2 4s in Vec. There's a 4 at the beginning of list because we did the push front. There's now 2 4s in list. So this and this do the same thing, but they didn't put the name in there. They didn't put push front in there because they wanted you to go on to Stack Overflow and be like, why is there no push front in vector? I am speed, exactly. So yeah, Python is not designed for speed. Python will be 10 times slower than C++, kind of as a general rule of thumb. Java used to be that slow. I've actually got books on Java up on my bookshelf here. And the benchmarks on that for most of the numerical calculations is about twice as slow as C++. Notation was shorter in Python? Sure. Yeah. And Python's probably less verbose. Java's more verbose. There's more typing. A lot more typing in Java. I always joke that Java has an agreement with the keyboard manufacturers because they wear out keyboards typing Java. Buffered reader. You have to type 3 things and nest them inside of each other to do anything. Python's really nice. Why are they switching to Python? Who is switching to Python? Look at this speed. I know programmers are recommending you to learn Python. Yeah, I mean, if you're a new programmer, Python. Yeah. So okay, I shouldn't criticize Python that way. Python's fine. Python's fine. If you don't care about speed, Python's fine. It's got really nice libraries. You can graph things very easily. There's things like PyTorch and NumPy and Pandas that do a lot of data science stuff. You can do this and do stats and graph them in like a line of code. And it's nice. Basically I would recommend Python for quick prototyping, but if you're going to do anything that needs performance, C++ is where it's at. And C++ is also kind of just it's important to learn for a lot of reasons, but like it doesn't hide. Like Python runs on top of an interpreter, and so there's kind of this disconnect between your program and what's actually happening on the machine. And with C++, with things like pointers and things like that, you actually kind of understand what computer architecture is doing.
There's this really funny part in in the book I was just reading. It's really funny.
Maybe they want more people to adapt to it. I don't know. YouTube said they switched to C++ when I job shadowed there. Yeah. So, C++, especially modern C++, because this is modern C++. Old C++, was rightly criticized for being hard to use. Okay, so that's a list. Basically, what's the downside to a list? Well, what if I wanted to output element? If I wanted to output vector.at 3. What is the running time? Big O running time of this. This is big O what? Big O what? How much time does it take to output element 3 of a vector? Right? So how much time does it take to output element n of a vector, let's say? Doesn't really matter which one. It's order 1. Yeah, very good. It's order 1. Because it just, in order to access element 1000 out of a vector, there's a pointer, and then you add to it 1000. Like if you're trying to access element 1000, you add to it 1000 times the size of an integer. An integer is size 4 on our machine, so it'd be a pointer, which is an int, plus 4,000 bytes. So it's a multiply and an add. It's constant running time. Okay. With a linked list, it is not. So with a linked list, it is not constant running time. If we were to, because there is no random access with a linked list. If you, this is the downside to a linked list. You can't just access element, 5. You have to go from the start, 1, 2, 3, 4, 5. If you want to access element n, you have to do n, right? So if you want to access list.at3, I don't even know if it has an at3. Doesn't work. Yeah, doesn't exist. Oh, maybe it does. Nope. Nope. Yeah, so you could do something like this. You could say list.begin plus 3, and that gives you an iterator. An iterator is like a pointer. I sometimes say it is a pointer. It's actually, it just works like a pointer. Invalid operations, binary expression, list, iterator. It doesn't like adding. Interesting. It should be a forward iterator, so it should be able to move forward. Whatever. The point is that you can't just randomly access element 3 out of a list. You have to go from the beginning to the end. And oh, yeah, you know what? I know it. Let's do this. For int I equals 0, I is less than 3, I plus plus. Auto iterator is equal to list.begin. So I'll get a pointer. I call them pointers because they work like pointers. Again, don't sue me for not being technically precise. So I'm going to get a pointer to the beginning of the list, and then 3 times I'm going to say iterator plus plus, because it's because you can't actually add 3 to a list pointer. You have to do the plus plus operator 3 times. And again, that's because they don't want to hide a slowdown, right? They want you to be very clear. You are doing an order n operation, right? And there's find. You could use find to find it and stuff like that. But this will move the thing 3 elements to the right, and then we can see out that. So we have a pointer to the first element. We move it to the next element in the linked list. We move it to the next element in the linked list. Move it to the next element in the linked list, and then we dereference the pointer and output the value there. So list, we'll just call it list.at3 for symmetry's sake. And you can see 0, 1, 2, 3, so it should print out 3. Good. Good. Okay. And so this is, list.at3, which doesn't even exist, is order n. So, which linked list is better? I mean, which data structure is better? Vectors or linked lists? What do you guys think? Ephraim says, depends what you're doing. Brian Gonzalez says linked list. Benny Hoban says linked list. Hazelton says yes. I mean, it just looks like a list is a vector with more features. It's a list with more features that you can't randomly access things out of it without doing an order in operation. So, Connor McCohen, yes. Edgerlin, it's a vector with push front and pop front. Depends. Muya says vectors are better. Scandin, can you do pushback for a list? Yes, you can. So you can do list dot push back 10, and that works with a vector as well.
Are they going to do the benchmarking assignment later, where you actually compare all the?
That's the plan. So yeah, you can push back on a vector, and you can push back on a list as well. Yeah. Good question, Emma. So you can see we've added 10 to the vector, and we've added 10 to the list. So these two things are essentially the same. Like, it's not like, you know, we're really stuck, you know. But what changes though, is the difference between a vector and a list is what is fast and what is slow. That's the difference. Okay, it's not like you can't, you know, insert something at the beginning of a vector. It just becomes expensive, right? Like you can, you know, if you want to insert something at the beginning of a vector, you can do it. It's you're going to pay for it though, right? And so so let's say you have an application that every once in a while you have to insert something at the beginning. Well, you know, maybe a vector is still a good idea because every once in a while you just pay the cost to insert at the beginning. I don't know. And so the people that were saying it depends what your application is are exactly right. There is no best data structure. There is no best data structure. It depends on your application. And so the trade-off is linked lists. Linked lists are order 1 for push front. Vectors are order n for push front, or insert. Vectors are order 1 for random access. .at. Linked lists are order n for random access. Okay. So the question is, what are you going to do more of? Are you going to be using .at more? Or are you going to be using push front more? Okay. And with linked lists, .at for accessing things in the middle of the data structure. Okay. Accessing things at the front, accessing things at the end are perfectly fast for a linked list. And also if you just need to traverse the whole thing, this is order n and that's order n. So if you're going through a linked list in order, it's just as, you know, just as cheap as a vector. If you're doing something like this, where you're starting at the beginning and going to the end, which you do, like if you're just printing all the elements out. You start at the beginning, go to the end, print everybody out. Same cost. But if you need to just randomly access element 3, element 50, element 100, element 1000, element 2, then vectors are order 1 for those operations, for randomly pulling things out of the data structure. Linked list, you're going to pay through the nose for it every time. So there's no answer. There's no answer as to what's best. It just depends on your need. What do you need? What does your algorithm need? I should say, not what you need. What humans need is food and drink and sleep and love and attention, right, Ada? Mm-hmm. Yep, she nods. Clothing, housing, oxygen is pretty important, I hear. Here, oxygen is important. Do cloud storage like AWS use C++ since they have to access information? Yeah, Google's really big on C++. They usually present at CPPCon every year. Go by the name of Cyrus, I think his name, at Google. He always gives good talks. CPPCon, Cyrus from Google. I don't remember his name. He gave a bunch of good talks that I've watched. Yeah, so like Facebook is heavy into C++. Most game engines are written in C++. Unity switched from C++ to C#. That was a big story. But Unreal Engine's written in C++. Any high frequency trading, if you're interested in doing game stonk stuff. If you want to work for Goldman Sachs and things like that, you're going to want to probably know C++, because anything that's where speed's important, which is a lot of areas, C++ is your choice. Is C# better or worse than C++? Again, there's no good answer for this, right? Like C# does some things a lot nicer than C++. But it's managed code. Managed code means that it runs in a virtual machine, which means it's slower. It's going to be slower. There are optimization techniques that work on virtual machines, like jitting and things like that can speed it up. But given infinite time to optimize, a C++ program will always be faster than a C# program. That's according to my friend at Microsoft, who's a big C# guy. That's like literally a quote from him. But he says, who has infinite time? And so with C# you can get something up and running, and some things are really easy to do in C#, like connecting to a database. So in C# you can, inside of your C# code, have a SQL query, and it returns a data structure, and you iterate across it and analyze it, and you can do that a lot faster than in C++. And so it just depends. My answers for everything are going to be, it depends. But there's a difference, right? Like between linked lists and vectors, there's a difference. There's a difference between C# and C++. And so it depends on your needs. It depends on your needs. If you're making a video game, I would probably do C++. If you make a video game in Java and the garbage collector kicks in, your frame rate will hitch. And nobody wants to have a video game where it stutters, right? So I wouldn't, in C#, they have a special version of C# for Unity that works on those issues. But like, I'd probably write a video game in C++. C++ is the master language. Yeah, I don't know. Like, I don't even think that C++ is hard to learn, honestly. Like, is this hard? Like, is that hard? Like, I don't know. I don't think it is. Make a vector, make a list. Like, I don't know. What do you guys think? Is this mind blowing? Is this causing your brains to crash? You should make a book. I will buy it. Thanks. I give away everything for free. So, I mean, what do you guys think? Like, you can, if you want to use the standard library stuff, all the standard library stuff, Sort doesn't work. Sort does not work on a list. That's actually one important thing. Sorting is different. Because sort requires you to be able to randomly access things inside of it. So if you wanted to sort the vector here, we can do sort vector.begin, vector.end. If we wanted to do the same thing here, sort list.begin, 3s list.begin to list.end. Doesn't work. Because sort requires being able to randomly access elements in it. So if you want to sort a list, you cannot do it that way. You have to do list.sort. Okay. And then that's how you sort a linked list. Sorting is different. This is the linked list specific version of sorting. So it has its own special sort algorithm. When C++ is a hammer, everything looks like a thumb. Yeah, it's a great phrase. Hit yourself over and over again. So you can see we sorted this properly. We've sorted this properly. Everything is the same, right? So that's you know basically everything you do with the vector you can do with the list. The question is trade-offs, like what do you want to have fast? What do you want to have slow? Okay. So if you need to randomly access things, use a vector. If you need to add things and delete things off the front, use a list. Okay. So is that easy enough for you guys to understand? We're going to learn something called a deck, which is kind of both a linked list and a vector, which is kind of in between the two. A deck, D-E-Q-U-E, yeah. Decks are basically linked list vectors. And you can push and pop off the front, but they have faster random access. So they kind of sit in between the two. A deca. Linked lists are good for things like menu setting screens, since you go back and forth via buttons. Yeah, if you're going to be arrowing up and down, then you can iterate through a linked list as quickly as you can a vector. But what if you click on option 5, then you gotta go through it that way. So in practice, I use vectors as my go-to data structure, and then if I need something else to be faster, then I'll switch out a vector for something else. And usually, honestly, I'm not going to use a linked list. I use a deck instead, because decks are better than linked lists, I guess. That's one way of putting it. So the decks are kind of a nice compromise between a linked list and a vector. Please don't say map. Maps are awesome. Maps are great. We'll learn maps later on. But maps are great. Unordered maps are even greater most of the time. So, sets and maps and unordered sets and unordered maps and multi-maps and multi-sets and unordered multi-sets and unordered multi-maps. The 8 different variations of basically the same thing. We'll learn those in a later lecture. This is the topic for today, though. Do you guys understand? Could you guys answer a quiz question on this? What is fast for a vector? What is slow for a vector? What is fast for a linked list? What is slow for a linked list? Could you guys answer that? Okay. All right. So that's it. You guys learned a new data structure today. You're in a data structures class. You just learned your first new data structure, unless you didn't know vectors before. That's it. All the standard library functions, basically, you just use them. Just things like sort and probably random shuffle might not work. Anything that requires random access won't work with a linked list. But yeah, by and large, if you want to add up all the elements in the linked list, you just use accumulate, and it'll add all the elements up. Like find works fine. It's basically usually it's just a matter of changing one word, and then all the rest of the code works the same. It's the beauty of the standard library. Behind the scenes, very different things are happening. You've got pointers, and the pointers are moving around and jumping to different spots in memory, and in a vector, it's a contiguous block of memory, and behind the scenes, completely different things are happening, but the interface, and that's why ADTs are so important. You have an interface, and you just have people using your code. They don't know what's happening behind the scenes with all these pointers and all this stuff. Just the interface is the same, and if you want to switch out a vector for a list, you change one word, and it'll work mostly. So data structure understanding skills +1. Yep, you got a new data structure. It's not going to be the last. We're going to go through queues, stacks, binary search trees, and hash tables in this semester. Maybe heaps. We might get to heaps too. We might get to treeps and tries and some other stuff as well. But this is the first new data structure for you guys. Okay? So that's it for today. Peace out, and have a great weekend. Get fizzbuzz TDD done by Monday, I guess. And is it a long weekend? Is it a long weekend? Do we have Monday off? No? Okay. All right. So I'll see you guys on Monday then. I never know when there's holidays. Students always know when there's holidays more than me. I'm always willing to teach. But. All right. That's it. See you guys.